Hi everyone, this is Edward Lamb from Monash University. This talk is about large neighbourhood search for temperature control with demand response. In this paper, we study a real problem in the energy domain. We have several buildings connected to a microgrid. A microgrid is a small electrical grid that is close together. On very hot days, there is not enough power to run the air conditioning systems of all buildings at the same time, so we want the microgrid to centrally control when the buildings should turn off their air conditioning. For example, some buildings may have better insulation than other buildings, so these buildings can run their air conditioning for less time overall. We want to control the air conditioning systems in all buildings so that the occupants are comfortable. We apply machine learning and optimization to the problem. We collect temperature data from each building and we train the neural network on the temperature data. This model predicts the next temperature given the current temperature and some environment inputs. And then we embed the trained neural network into a quadratic programming model. This optimization model copies the neural network for each building and each time step, and then we optimize over all buildings and time steps to decide which buildings should turn on their air conditioning during which time step. We also developed 6 neighborhoods in a large neighborhood search. Each of these neighborhoods aim to improve the solution in a different way. We solve the optimization model using constraint programming and mathematical programming with and without the large neighborhood search, so we have 4 methods in total. For constraint programming, we use G-code, and for mathematical programming, we used Gurobi. Our experiments show that LNS in constraint programming finds the best solutions. Now let's take a look at the details. This is the motivation for the study. On the right is a picture of the Monash Microgrid. This microgrid connects 20 buildings at the Clayton campus of Monash University. Some of these buildings are teaching spaces and some are student residences. These buildings consume up to 3.5 megawatts of power. It also has 1 megawatt of solar generation and 1 megawatt hour of battery storage. It also has 2 electric vehicle chargers. The electric vehicles can also serve as another battery storage and power the microgrid when they are sitting idle. The Monash Microgrid is one part of Monash University's Net Zero initiative. The university aims to have net zero carbon emissions by 2030. This project won the United Nations Momentum for Change Award in 2018. This is the background to the problem. In Australia, the temperature can get to around 45 degrees Celsius or 113 degrees Fahrenheit during the summer. On these days, there is not enough power for everyone to turn on their air conditioning at the same time, so utilities will ask large customers to reduce their power usage in return for payments. Utilities usually send out notices of demand response events 24 hours in advance based on weather forecasts. The picture on the right shows the power consumption of a building over a typical day. The black line is the normal power consumption of the building. The red line shows what happens if there is not enough power during the peak period. Some appliances will be abruptly cut off. We want to avoid this situation. We study a way to achieve the blue line. We want to shift power usage to earlier in the day when it is not as hot, so we have enough power to run essential appliances during the peak. For example, air conditioning can be turned on earlier to pre-cool the building and let it rise in temperature during the peak. The ultimate aim is to get to the green line. After upgrading some appliances, we don't need to consider this issue at all, but that is much farther into the future. We study the problem of centrally controlling the air conditioning system across all buildings connected to the microgrid. During peak periods, there is a limit on the power supply. We want to decide which buildings should use this power to keep its internal temperature comfortable for its occupants. We want to maintain the temperature within some comfort bounds so that the occupants are comfortable, and we cannot exceed the power supply at any given time. We use a predict and optimize approach. We first collect temperature data from the buildings, but actually some of the buildings are not yet collecting data right now, so we use a simulator based on parameters from the design and construction phase. So we use simulated data right now, but we will use real data from the buildings when the data is available. We train a machine learning model for each building to approximate the temperature function. And then we encode the trained weights into an optimization model. We use the optimization model to control the air conditioning systems, and we need to ensure that the comfort and power constraints are satisfied. The temperature transition function is what we are trying to learn using the machine learning model. It tells you the temperature in the next time step given the temperature in the current time step and some environment inputs. The temperature is governed by physical laws, and it can be modeled using differential equations, so we can discretize it using finite difference and then encode those equations into an optimization model. But there are many different temperature models to choose from, so it's easier to just train a neural network, and then we don't need to worry about which temperature model to choose. We used this neural network architecture shown on the right. We train one of these for every building. It has 3 Boolean decision variables as inputs, xoff, xcool, and xheat. Only one of them can take value 1, and the value 1 means that the air conditioning is either off, cool, or heating in time step t. We have 4 environment inputs, the indoor air temperature, the indoor mass temperature, the outdoor air temperature, and the solar irradiance, which is a measure of how much the sun is shining through right now. We have 3 outputs. The outputs are the air and mass temperature at the next time step, and it also outputs the power consumption for running the air conditioning according to the inputs. We will optimize over this value of how much power the air conditioning systems are consuming. This is the optimization model. The objective function is quadratic. It comes from penalizing temperatures far away from the comfortable temperature. We have the blue constraints, which encode the neural networks. 1 neural network for each building and each time step. We have the yellow constraints, which says that the air conditioning must operate in one mode at a time. And finally, we have the green constraints, which limit the total power according to the demand response events. This green constraint is quite simple. It just sums the power as predicted by the neural network and puts a bound on the total power in the right-hand side. So this model is deterministic for now, but we can upgrade it to some kind of stochastic in the future. The standard approach to this kind of problem is multi-agent reinforcement learning, but this Predict+Optimise method has a few advantages. The buildings are completely independent. Each building is independent in the training phase. The neural network of each building is trained independently, and then they are encoded into the optimization model, so it is very easy to add new buildings into the model because the buildings don't interact. In reinforcement learning, whenever the costs change, you need to retrain the neural networks because the reward function changes. We don't need to retrain using this method because the costs are in the objective function in the optimization phase. We only need to retrain when the physical building changes, such as when we add more insulation into the building. It is also easy to add new constraints into the optimization model. Maybe there are new requirements in the future which we can simply add as new constraints. We first tried solving the model by inputting it directly into a solver, but it was too hard to solve exactly. So we tried a large neighborhood search. So large neighborhood search is a type of local search. In large neighborhood search, the search algorithm calls subroutines known as neighborhoods on the current incumbent solution to improve the current solution. A neighborhood fixes the variables to the values in the solution and doesn't fix the remaining variables. A large neighborhood search then calls the solver on the unfixed variables so that it only searches over these unfixed variables. There is some randomness in the neighborhoods so that they don't search on the same variables in every iteration. The search algorithm then calls the neighborhoods until it reaches a time limit. It is best to design many different neighborhoods that fix different subsets of the variables so that the search can explore different parts of the solution space. We developed a large neighborhood search with 6 neighborhoods. Each of these neighborhoods target a different cause of suboptimality. The first neighborhood is called the cool-off neighborhood. This neighborhood aims to turn off cooling when it is too cold. It first fixes all the heating, and then it finds a time step that is colder than the comfort temperature, and it relaxes the cooling and off variables surrounding this time step. This neighborhood aims to switch around the cooling and off time steps. The picture on the right shows that the cool and off is pushed later one time step. We also have an equivalent neighborhood for heating, so the cool off and heat off neighborhoods are the first 2 neighborhoods. The third neighborhood is the flip neighborhood. This neighborhood aims to remove alternating sequences of heating and cooling because these sequences waste a lot of power for no reason. It begins by finding an alternating sequence of heating and cooling, and then it relaxes some time steps surrounding the sequence. The picture on the right shows one of these sequences of alternating heating and cooling. These sequences arise when the temperature is hovering around the comfortable temperature. Earlier in the search, the neighborhoods try to cool and heat when the temperature is alternating below and above the comfortable temperature. The flip neighborhood aims to turn off the air conditioning during these sequences. The next neighborhood is the Precool neighborhood. This neighborhood tries to cool down a building before the occupants arrive. It finds a time step that is cooling but still too hot, and then it finds an earlier time step that is too hot but is either off or heating. It then relaxes all the time steps in between. The picture on the right shows that the building is initially too hot before it starts cooling. So this neighborhood turns on cooling earlier so that the building is comfortable when the occupants first arrive. We also have an equivalent neighborhood for preheating. The last neighborhood is the on neighborhood. This neighborhood tries to turn on cooling or heating. It finds a time step that is off and is either too hot or too cold, and then it relaxes the time steps surrounding this time step. It is essentially the opposite of the first 2 off neighborhoods. There is only one on neighborhood but 2 off neighborhoods. This asymmetry arises because we have 2 on modes, the cooling and heating, but only one off mode. Some buildings are not yet collecting data, so we generated 20 buildings similar to the buildings in the real microgrid, and we generated 600,000 data points per building. The parameters come from the plans of the buildings. We trained 3 sizes of the neural networks using TensorFlow, and we found that the smallest one is almost as good as the largest one, so we used the smallest one to make the optimization easier. We randomly generated temperature data for 504 instances with 48, 96, or 192 time steps. Each time step is 5 minutes long. Some of these instances have extremely cold or extremely hot temperatures for capturing the real environment in Australia. We use Gurobi as the mathematical programming solver and G-code as the constraint programming solver. We use the complete branch and bound search, and then we also implement the large neighborhood search and the 6 neighborhoods in both Gurobi and G-code. Each solver is run for 30 minutes. This is a cactus plot that shows the number of instances that each method solves to under a particular objective value, so lower is better. G-code with LNS finds the best solutions. It is the only method that finds feasible solutions to all instances. All 4 methods are initialized with a greedy solution at the start. Even given this initial solution, Gurobi cannot activate this solution internally, so we can see that constraint programming is much better at this problem than mathematical programming. We think this is because it needs to find a basis for this initial solution, but this task is already very hard. This plot shows the solution to one of the instances. There are 2 periods when the building is occupied. This is shown in light grey. One period is in the morning and one period is in the afternoon. Within the afternoon period, there is a sub-period when the power is limited. This is the dark grey area. The red line shows the solution from the optimization model. The decisions coming from the solutions are then input into a simulator to verify that the temperatures appearing in the solution accurate according to the simulator. The temperatures from the simulator is shown in the black line. You can see that the red line and the black line are very close together. This means that the model is accurate. We use a set point of 22 degrees. This means that it optimizes for the buildings to be near 22 degrees when the occupants are inside. You can see from the plot that the model optimizes for comfort in the morning period, and then it turns off the air conditioning when no one is inside during the middle of the day, and then it turns it back on before the occupants return in the afternoon. But in the afternoon period, there is not enough power to run the air conditioning system, so the temperature increases while the occupants are inside. Our conclusions are that this problem is too hard to solve exactly. Constraint programming with large neighborhood search seems to be the only viable method. We also tried to get a lower bound by running Groby over a few days, but it only reported a lower bound of 0, which is useless. This means that the relaxations that Groby uses is much too weak. So in conclusions, the problem is much too hard to solve exactly, so we must use local search methods, and it appears that constraint programming with large neighborhood search is one of the better approaches. Thanks for listening.